Let's go through an example of doing the confidence interval for a mean, which uses the t-distribution. This is taken from some supplementary materials for the book. It's going to be very similar to their step-by-step example as well. And we discussed the start of this in class. And I said one thing that was actually rather incorrect in class, so I'm going to correct that. A coffee maker is supposed to deliver 10 ounces of coffee on average per cup. It's okay if it varies a little from cup to cup. That's not a problem. But we don't want the average amount to be under 10, or else we think we're getting shortchanged. So how do we figure that out if we suspect we're getting shortchanged? Well, we fill a few cups. So let's take a random sample of 20 cups. Here's the numbers we get. Anywhere from 9.7 to, 9.5 actually, to 10.2. And we'd like to know, is this evidence that we're being shortchanged? We could either do that as a hypothesis test, or we could make a confidence interval for what we think is the actual mean. Okay, so let's do that. That's a little bit more straightforward. We'll do the hypothesis test version next, maybe another video. So if we want to make a 95% confidence interval, what is it for? It's for the actual mean, what you'd usually call the population mean. Imagine this is a sample of a few individuals out of a bunch of people, and we want to know the actual mean for the population. Here, it's if we let the coffee maker run for its entire lifetime, and we looked on average, what does it give over the entire lifetime? What's that going to be? Okay. In particular, we'd like to know how much margin of error there is. There's going to be a very obvious thing to do to start with to figure out, even to start, whether we think it's shortchanging us. And that's just take the average of these 20 numbers. We're going to take the sample mean. And we want to know how close is that likely to be to the actual mean, which we'll never really know. Okay. So we want to figure out the margin of error. First of all, there's some conditions to check, as always. It has to be a random sample. Well, we've been told it's a random sample. We're going to trust that it really was random. We're going to assume it's well enough to assure independence of the individual values. In particular, it certainly wouldn't be a good random sample if it was just 20 cups in a row. Maybe if it's 1 cup every hour, 1 cup every day, or something like that. Okay, randomly sampled. And so we're going to trust that it was done well enough to assure independence. That's something that's crucial. We need the 10% condition in cases where you've got a finite population and you might actually risk actually double count, like counting the same person over again. Then that's going to be something we have to worry about. Are we sampling with or without replacement? And is that going to affect things? Here, this 20 cups is a very tiny proportion of all the cups the coffee maker could make. Okay, so that's okay. Here's the new condition, though. Instead of the success-failure condition, which doesn't have any analog here, this is not about proportions, yes or no, Bernoulli kind of stuff. We need the nearly normal condition. Turns out we're going to push the limits of the ideas of things like the central limit theorem pretty far to where we'd really like to know something about what distribution do these come from. Is it true, if it was true that a coffee maker tends to give you a little under 10 ounces, but then sometimes it gives us 15 or 16, and we've got a really skewed distribution, that would make the methods we're about to use invalid. Now, we don't know exactly what the coffee maker gives us. If we knew that, we wouldn't have to ask this question. But we can at least look at the histogram of this data and see if it has any red flags. Okay, so I did stat edit. Okay, I'm not going to show you live because I'm trying a different version, but we know how to do this on the calculator. Stat edit, enter it in, and then I did a histogram. Okay, you go to stat plot, set up the histogram. We know how to do that. Looks pretty good. It's unimodal and symmetric, and so this is reasonably normal. It turns out that when the sample size is greater than 15, we only need just vaguely normal, and we just check unimodal and symmetric. Okay, this is a pretty tricky thing, something we're not going to prove about why is it 15. Well, it turns out from experience or just a lot of more mathematics, you can show that it's going to work as long as it's vaguely normal to start with. Okay, so as I said, there's no analog of the success-failure condition to check. This isn't yes or no stuff. It's numbers. It's quantitative data, not categorical. Okay, so here's what the natural thing to do is take that data table, enter it in. Let's look at the sample mean, 9.845. Here it is in a little nicer print. Okay, so here's guess one as to what might be going on. Okay. Well, actually, guess one is that it looks like it's shortchanging us. This is definitely less than 10. But remember, if this was like 9.999, we wouldn't say, oh, it's obviously shortchanging us. We need to have some measure of the random variation. Okay, so The next guess, let's call that guess 1, is, okay, we compare 0.155, and we need to have some rough estimate of how much variation is going on. Oh, well, we have some data that might tell us roughly how variable the coffee maker is. Now, it's not going to tell us exactly how variable it is, and that's where the real interesting part lies here, where the new part lies. But it seems to be that it varies on a scale of 0.1, 0.2, 0.3, something like that. We can quantify that using the one-bar stats. Back to here. Notice the SX 0.1986 up here, and I've got it down here. Okay, so here's the mistake I made in class. It seems like 0.155 is pretty small compared to 0.1986. So maybe this variation that we're seeing isn't very significant. Wait a minute. This is a really important issue. Okay, I'm kind of almost glad I made the mistake. Okay, to highlight this. The variation we're looking at is the mean is 9.845. We've taken the mean of 20 different individuals. If I look at S here, that is how much those individuals all differ from each other. That's the individual standard deviation. So this measures the variation of all the individuals. But if I looked at a group of 20, and another group of 20, and another group of 20, and another group of 20, they wouldn't be predicted to vary nearly as much as 0.2 from this kind of value. Okay, so the variation of the mean, this is the sampling distribution of the mean, the sample size 20, it's a lot less than the variation of individual data values. Namely, I should take this standard deviation and divide by root 20. That would give us a rough estimate of standard deviation of 0.0444. Now, guess 2, 0.155 looks pretty big compared to 0.0444. I think maybe they're shortchanging us. We need to quantify that, and we need to be precise. Here's the issue, okay? Guess 2, basically, is let's assume everything's modeled by a normal model with a known standard deviation. Well, you know what? I don't know the standard deviation. I shouldn't be using the sigma over root n formula when this is an S. This is just an approximate version of what the actual standard deviation might be. If I looked at 1,000,000 coffee cups and took the standard deviation of that, then this would be a rock solid number. As it is, it's just gotten from a sample of 20. Okay, so you might think that's the end of the line. We're stuck. Okay, the nice thing is that there's going to be a fairly simple correction to correct for the fact that we're, instead of using the sigma, which is unknown, we're using S. Okay, now let's continue with guess 2 for just a second. Let's finish it off just to emphasize sort of the parallel to what we're really going to do and what we might naturally do from before. Okay, so this stuff here is not quite right, what I've got highlighted. There's one particular error that we're going to make. This step is pretty good. We're going to try to get the sigma over root n, which would be the real variability in the sample, and we're approximating it by S over root n. There's that 0.044 number again. Okay, here's the key thing. If this were a normal, we could pull out a 95% confidence interval by setting z star as 1.96. That's what we're going to have to change. Okay, because it's not really normal. If we did that, what would we do? We'd multiply that by the standard deviation. We'd say, here's the ruler in this case, a measure of the variability. We're going to go about 2 units of the ruler on either side to get our idea of the margin of error. Okay, here's what we do to correct that slight error. We're not going to use the z star. We instead use the t distribution. They talk about that in the book, about a slightly wider, fatter-tailed version of the normal distribution. Okay, I'll have a picture of it in just a second. In terms of the calculator mechanics, we can go to inv t. This is on the distribution. Let's just go to the distribution button. We go to 4, which is inv t, and then we plug in 0.975 and 19. Why 0.975? Well, remember, to get a 95% confidence interval on an inv norm, we would use 0.975. It's the whole issue of one tail versus two tail. The additional thing here, as they point out in the book, there's actually many, many more than one t distribution. It actually depends on what the sample size is. So it's a little more complicated. You just have to take the sample size minus 1 and put that in for the degrees of freedom. It's not something I'm going to emphasize a lot. The main thing I'm going to emphasize is it's a miracle that we can even do this at all. We can go ahead and just fudge and say, I don't know sigma. I'm going to put in this thing that's an S at all. It's a miracle that we can do that. So it's not too much of a price to pay for a tiny bit more complexity. That we actually have to say, oh, by the way, here's our sample size. Turns out sample size minus 1 is the crucial number. And then it gives us the right t distribution. So Here's our analog of the Z star, 2.093. We're going to call that T star 19. Okay, so here's the picture I promised. If it were a normal distribution, let's say the dotted is a normal distribution. I know it looks a little bit weird, but that's okay. Here's what we would do. We would look at our average that we got from our sample, 9.845, and we would look for the Z star, which is 1.96. That means that 95% of our probability is within from minus Z star to Z star. Okay. Because the T has somewhat wider tails, that would, if I put the value here, 1.96, I would get more than 2.5% over here. That's what I want. In both cases, for a 95% confidence interval, I want exactly 2.5% of the error of the probability here and 2.5% symmetrically over here. Because it's wider, the T star is going to push up a little bit. Okay, I am going to have a bigger confidence interval. I'm less precise about my answer. That's always what's happening. Whenever you try to fudge something, remember we're doing this fudge, approximating sigma by S, it would be pretty weird if we got more precision out of that. And so that's one way to understand why this has to go this way. So the T star is a little bigger than the Z star. It's 2.093. But then, from then on, it's the same. I use my ruler, 0.0444. That was my standard error here. I go 2.093 of that units, 0.0929. And so the 95% confidence interval is 9.845 plus or minus 0.0929. Or in other words, 9.75 to 9.94. So here's what I think is a pretty good guess as to, on average, how much coffee I'm getting. And I'm 95% confident that the true value for the mean, if I did 1,000,000 coffee cups, would show up between 9.75 and 9.94. Now I can be pretty confident that we're being shortchanged. There is something slightly wrong with this coffee maker because this interval stays pretty clearly away from 10.0.